we are going to discuss about the electrochemical process. This is exactly reverse to what you have studied so far. In the previous session, we have seen that the conversion of electrical energy into the chemical energy is what we referred as electrolysis process. Now, coming back to this process, this is actually the conversion of the chemical energy into the electric energy. Now, we need to understand little bit about this chemical energy. Now, we know that when a spontaneous chemical reaction take place, for example, I will consider a hypothetical chemical reaction taking place in solution. Say these are all the substances that are involved along with their stoichiometric coefficients. Now, when this process is taking place, when this chemical reaction takes place, and if I say this is a spontaneous process that take place on its own, then we expect here that there is decrease of Gibbs free energy of reaction. What I mean to say here is that the delta G, that is the change in the free energy of the reaction, that is equal to the total free energy of the products minus the total free energy of the reactants put together will become the Gibbs free energy of the reaction. So, one can expect here the spontaneity of a chemical reaction when the situation is like this. This is your reactant free energy and this is product free energy, and the difference is what we call as delta G, which is found to be less than 0 or negative for a spontaneous process. So, now what I am going to do is I am going to convert this decrease of free energy into the electrical work. So, here we understand that the energy format, that is decrease of free energy, you referred it as negative of delta G. The negative sign indicate that it is decreasing, is being converted into the electrical energy. Now, when I am writing electrical energy, I know that I involve the total charge into the potential, which we refer here as the electromotive force, because here we are creating not voltage or potential, rather we are creating the electromotive force by creating a potential difference among the metal that you are dipping in the solution and the species which is already there in the solution. So, here by doing that, so suppose n mole of electron are involved in that particular process, and the charge on each mole is 1 Faraday, and the total EMF of the cell, if I consider that as the E cell, this is found to be the situation. Now, when I am doing the same in the standard conditions, under standard conditions, that is temperature is 298 Kelvin, and under atmospheric condition we refer this as delta G naught is equal to. So, now we should talk about this E naught, that is standard potential of a particular electrode to participate in the oxidation or reduction process. Under standard conditions, we represent this as the delta G naught along with E naught of the cell. So, here in order to understand the logic of this chapter, we need to focus upon the E naught, that is nothing but the standard potential of a particular electrode to undergo oxidation or reduction. So, here we are going to discuss about the electrode potential, which we represented as E of the electrode. Now, when I am calling under the standard conditions, we call it as standard electrode potential, say E naught. Now, this important definition is divided into standard reduction potential as well as standard oxidation potential. Now, we need to understand why this potential term is being used. Now, if I take a metal ion combination, for example, the aqueous solution of zinc plus 2 is immersed a zinc plate, we can expect here that as soon as the metal zinc comes in contact with the Zn plus 2 ion, due to the phase difference there arises a potential. The potential of these two to interconvert into each other. I mean, so we can say that either zinc has the tendency to get converted into Zm+2 or the vice versa is possible. So, here when the metal is being brought in contact with that complementary ion, it need not be the same always, my dear students. Here one has to notice that if I am taking say the aqueous solution of the acid, that is nothing but the H plus ions, when I am putting a platinum rod inside, this is not just sufficient to develop the potential difference. One has to understand that we need to bubble in the H2 gas, and then only the electrode is said to be the complete one. Now, we need to immerse the relevant electrode which is complementing along with any other species the existing ions that are present in the solution. So, due to the phase difference, one can anticipate here the potential to be originated. So, there are two ways in which this could happen, that particular species may have the tendency to undergo reduction, then we call it as reduction potential. If it is having any tendency to undergo oxidation, we would definitely call it as oxidation potential. For example, here this is taking place, which is indirectly hinting us that it is undergoing the oxidation, whereas if I immerse the copper rod in the aqueous solution of the copper sulphate, one can anticipate the reduction by grabbing the electron that are left over at the other electrode. So, here this is how the tendency to undergo whether oxidation or reduction is being developed over here. Now, the important part is that if I represent, for example, any metal with the valency say X getting converted into M or vice versa, if it is undergoing the reduction, then we call it as E naught M plus X slash M, whereas if it is undergoing the oxidation potential would be represented as E naught M to M plus X, and one has to understand that these two are contradicting with each other in terms of the sign convention. If, for example, the E naught of this, that is the standard reduction potential of copper ion, is if I say 0.34 volt, then its oxidation potential when I denote, I would call it as minus 0.34 volt. That means, we say that this has the tendency to undergo the reduction. Now, when I am writing the oxidation potential of zinc, it has been found that it is around 0.76 volt, indicating that this has the tendency to undergo the oxidation, whereas its reduction potential value will become negative, then it has no tendency or less tendency to undergo any sort of reduction. So, here on the whole, if I want to construct the electrochemical cell, I should ensure that the species say zinc and Zm+2 complementing each other, whose concentration is C1 molar, is connected to any other species which has got the tendency to undergo reduction, because we have just seen that a zinc couple has the tendency to undergo the oxidation. Now, when I am connecting these two through a voltmeter or ammeter, I can anticipate here the flow of the electrons. So, here copper is immersed in the aqueous solution of copper plus 2. One can expect here that since we found that the oxidation potential value is high, so this will undergo the oxidation, the reduction potential value is high, so this will undergo the reduction. Now, we say that when zinc undergo the oxidation, this takes place, and the electron that are passing through the external circuit are moving into the copper, and those electrons will be absorbed by the copper ion to get converted into the metal. Now, when I am writing overall the reaction, the overall cell reaction in this cell is zinc is replacing the copper from the solution by participating in redox reaction. So, here you can see that zinc metal has replaced the copper ion from the solution. So, this is how the overall reaction is taking place. So, here if you think that the cell is complete and we are going to produce some electricity out of this, that means we are making a blunder here, because this circuit is not yet complete, for the reason that when this process takes place of the zinc ion flowing into the solution, zinc flowing into the solution as zinc ion, and copper plus 2 is getting deposited on the surface of the metal, you would certainly guess here that there is increase in, here you can see the positive charges are coming in, there is increase in the positive charges at the, you can see here electrons are released here. So, this is the negative electrode, but oxidation is taking place. So, here we call it as anode. This is completely contradicting with what you have seen in the electrolysis, where we call this negative electrode as cathode. Now, the electrons are being grabbed by this, so it is cathode, the positive electrode. So, here if we see the process in which there is accumulation of the positive charges at the anodic side, similarly the copper ions are going and depositing on the surface. So, there is increase of the negative ion concentration at the cathodic side. This will prevent the further flow of this zinc into the solution, and here the sulfate ion that are excess in the solution may prevent the copper to get deposited on the top of the copper metal. So, in order to prevent this, we need to neutralize this, like we do earthing in the general electricity, like we need to neutralize the solution. There is accumulation of what? The positive charges at the anodic side, and there is an accumulation of negative charges because of the frequent deposition. So, in order to prevent that, we keep a U-shaped tube filled with a strong electrolyte kept in agar-agar jelly. So, here I am going to take a strong electrolyte like KCl, NaCl, NaNO3 etc. in agar-agar jelly, which allows the selective passage of the ions into the respective solution. Now, when I am keeping the strong electrolyte, one can anticipate here that since there is a increase of positive charges, I can expect here that from this the negative charges, I am going to say the chloride ions will flow into this to keep the positive charge inert. Similarly, the positive charges over there, that is the sodium or potassium ions, will flow into the solution in order to decrease the negative ion concentration. So, the circuit is said to be complete only when we fill this with salt bridge, and the whole set of arrangement is actually what we call as Daniell cell. So, here in this Daniell cell, we have seen that at anodic half cell there is oxidation. This is the cathodic half cell. This is overall cell reaction. Now, here the half cell that we have used is actually called as metal ion type.